Good morning. These are your 3.2 Part 1 notes about polynomial functions and their graphs. So I'll start by talking about the definition of a polynomial function. It's when n is a non-negative integer, and an integer just means a whole number. Non-negative obviously means it's positive, so non-negative integers are talking about numbers 1 and up. 1 and up. And let a1, an minus 1, a2, a1, a0 be real numbers. That just means everything but imaginary, with an not being 0. So here's what the function is defined by. F of x equals an to the xn plus an minus 1 x to the n minus 1 plus, and it goes on forever, a2 x squared a1 x to the first power, but we don't have to put it, and then plus a to the 0. So this is called a polynomial function of degree n. The number an, the coefficient of the variable to the highest power, is called the leading coefficient. So this part right here, the first number that has the highest power, is called the leading coefficient. And you'll see why that's significant in just a minute. Alright, so what are polynomial functions? So polynomial functions can be anything, any type of function, as long as, here's the restrictions, you cannot have square root of a variable. So square root of a variable and also you cannot have letters in the denominator. And just to clarify why, let me go back up here. So your exponent has to be a non-negative integer. If you think about square root of a variable, think about like square root of x. This is the same thing as x to the 1/2. Notice our exponent is not an integer because it's a fraction. So that's why we can't have square roots of variables. We also can't have we can't have negative exponents. So when letters are in the denominator, like 1 over x squared, that's the same as x raised to the negative 2 power. That's why we can't have letters in the denominator, because the exponent would be negative. So on these four, we're just going to talk about, is it a polynomial function or not? If it is, we'll just say yes. If it's not, though, let's explain why. So all you're looking for in this one, are there any square roots of letters? And the answer would be no, because this one has a square root, but only the 2 is under it, and that's fine as long as the letter is not. And then are there letters in the denominator? Well, there's not any denominators. There's no fractions here, so this one is a polynomial. And now let's talk about what would the degree be. The degree of this polynomial is going to be the highest exponent. So right here we have an exponent of 5, an exponent of 2, so the degree here would be 5, because it's the highest. And then the leading coefficient is the number beside the variable with the highest exponent, so our leading coefficient is that negative 3. Alright, so for the next one, you can see that this one is not a polynomial function. And the reason it's not is because of this square root of x. We can't have square root of letters or variables, so this one is not a polynomial function because square root of x. We can't have that. Alright, if you will, go ahead and pause the video and give my students just a little bit of time to try these on their own. So go ahead and try these on your own. Alright, so you could see that this one is not because we have a letter in the denominator. We have x squared in the denominator, which really means this is x to the negative 2 power. So this is not a polynomial function. This one is, yes, And what would the degree be? This one's kind of tricky. This one's in a different form. Notice how all of these are multiplied together, and in this one they were just added together. If we were to actually multiply this out, we'd have to multiply this 3x to the 4th times x, and all this stuff too, but we're just worried about the x's. So when we multiply letters, we do what with the exponents? Yes, we add them. So here the exponent is 1. Here the exponent is 1. So when we multiply x to the 4th times x, we'll get x to the 6th. So this degree of this polynomial is 6. And then for the leading coefficient, you just look at the lead number of all of them and multiply them together. So this lead number is -3. This number in front of x is 1. This number in front of x is 1. So 1 times -3 gives us a -3 for our leading coefficient. Alright, this just talks about smooth, continuous curves. That's what polynomials look like. They are smooth and continuous. There's no sharp points like this corner right here, and there's no discontinuity. So it doesn't break into like a piecewise function. So these are not polynomial functions. Polynomials, you can draw them without even picking your pencil up. They're smooth, continuous curves that go on forever. Okay, you'll flip your notes over. So now we're going to talk about end behavior and the graphs of polynomial functions. So the behavior of a graph of a function to the far left, so the very far left of your graph, or the far right, is called its end behavior. And it basically describes what your graph is doing at its endpoints, if it's going up or down. So although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound, goes on forever, as it moves to the left and to the right. The best way to determine this end behavior is using the leading coefficient, which we kind of practiced identifying on the last page, leading coefficient tests. Alright, so beside identifying our leading coefficient test, the other thing we will have to identify is if it is odd or even. Okay? So as x increases or decreases without bound, the graph of the polynomial function, we already talked about this, eventually rises or falls. That just means it's going to go on forever. In particular, here's the difference between even and odd. Okay? For odd, notice how the end of this graph is going down forever. The end of this graph on the right side is going up forever. They're in different directions. Like this arrow is going down. On this side, it's going to go up forever. That makes it odd when the end behaviors are different. So it's going down on this side, going up on this side. Same thing here. It could start by going up on the left side, down on the right side, but see how they're still different directions. That's what makes it odd. Okay, even functions are the same. They go in the same direction on both ends of the graph. See, these are both going up. These are both going down. So the end behavior is the same. That's how you know it's even. So that's the difference. Now, for odd functions, what makes it turn like this? If you have a positive leading coefficient, and y'all have to memorize these eventually. If it's an odd degree with a positive leading coefficient, it's going to go down as it goes left forever, up as it goes right forever. If it's odd but has a negative leading coefficient, it's going to go up forever when it's going left and down forever when it's going to the right. Alright, when it's even and positive, they both go up. So that's easy to remember. Positive, you're going up. If it's even and negative, you're going down. Negative down on both sides. So we're not going to graph right now. All I want you to do is practice finding the end behavior, and this is how we're going to find it for each one. This is in the factored form, just like, let me flip back, this example that we did on the first page. See how it's in factored form, where all of these are being multiplied together? So remember, for the degree, we have to add all the exponents. So this one has a 3. This is x squared. This is x to the first. So 3 plus 2 is 5, plus 1 is 6. So the degree of this polynomial is 6. And we don't care what the leading coefficient is, we just care about the sign. Because remember, we're just trying to decide if it's positive or negative. But first, since it's 6, it's going to be even, because 6 is an even number. So this is an even polynomial. Now for the leading coefficient, I just care if it's positive or negative. So look at the first numbers in front of x's, okay? So this one is negative, -4 in front. This is a positive 1 in front of this x, so I'll put a plus sign. This is a positive 1 in front of x, so I'll put a plus sign. And we'll circle these. And again, we don't care about the number. Just think about if we were to multiply together a negative and positive number, we would get what? If I were to multiply -1 times +1, that would give me a negative. So I dealt with these two. Now I'm bringing this one down. If I multiplied this negative times a positive again, I'd still get a negative. So basically, think about multiplying a negative number, a positive number, and a positive number. You would still get a negative number in return. So this leading coefficient is negative. We don't really care about what number it is. We just need to know that it's even, that our leading coefficient is negative. And so if you don't remember, you can look up here, even degrees with negative leading coefficient, this is how the end behavior will be. It'll be going down on both sides, so this is how we write it. And that's all you need to know. Alright, now let's look at one like this one, part D, where it's not in factored form. On this one, the degree is just the highest exponent. And again, the way you tell the difference between factored form and this form is nothing's being multiplied together here. This is in factored form because it's factored into different binomials and pieces. So this one, you can see that the highest exponent is 3, so the degree is 3. So that means this is what type of function? Odd, because 3 is odd. And this one, we don't have to worry about the sign of each one. The leading coefficient is going to be the one with the highest exponent. So leading coefficient here is 1. Again, we don't care about the number. We just care that it is positive. Leading coefficient is positive. So when it's an odd function, you know the end behaviors are going to be different. It's going to be going different on both sides. And now an easy way to remember this, besides just looking at your chart up here, think about your graph, like as it's going left forever, those are negative values, right? As it's going left forever, those are negative values on the x-coordinate. This is what I mean, like negative values here. So think about this as being negative going down first. And then as you go right, these are positive values, so you're going to be going up forever. And then an easy way to remember, if it was like leading coefficient negative, just do the opposite. So these are negative, but I'm doing opposite since it's a minus sign, so I'm going to go up, then down. Alright, let's do one more together. I'll just pick B. So the degree, I'm going to add together this 3, this 1, this 1. So 3 plus 1 plus 1, that's going to be 5, which makes it odd. And then I don't care about my leading coefficient, just the sign. So here's a positive 2, a positive 1 in front of this x, and a positive 1 in front of this x. So 3 positive numbers multiplied together is going to give me a positive leading coefficient. So this one's going to be the same as part D. It's odd and positive, so it's going to go down first, then up. Alright, Ms. Price, if you will pause and let my students go ahead and try C and E on their own. And then once they're ready, you can unpause it so they can check their work. Alright, so the degree of this one was 4. leading coefficient is positive, so the end behavior is up, up. So this one, the degree was also 4, so it's even. The leading coefficient is this -5, so it's negative, so your end behavior is going to go down, down. Alright, flip it over. Alright, so here is the fun part, finding zeros of a polynomial function. These you will have to do by factoring. Okay, and I know some of them are kind of weird. You might not remember how to factor some of these, so we'll work through them together. This one I noticed that none of them have anything in common, so I can't pull out the greatest common factor. But I noticed they have 4 terms. And when you have 4 terms, you always want to factor by grouping. And when you think grouping, you think of what symbols? Like parentheses or brackets or something like that. And that's exactly what you're going to do. You're going to group them off in groups of 2 with parentheses. Alright, then I want you to think, what is the greatest common factor of just these 2 terms? Like, what do they have in common? And that's going to be x squared. Now pull an x squared out of both of these terms, pretty much dividing. So x cubed divided by x squared is going to give us x. 2x squared divided by x squared is going to give us plus 2. And now look, what do these have in common? And the biggest number they have in common is a -4. So in parentheses, if I take out a -4, that's going to be x. -8 divided by -4 plus 2. And notice how these in your parentheses are the same. They should be if you've done it correctly. And I hope you remember this from Algebra 2. So now we can just bring down that x plus 2 that they have in common. And then whatever's left on the outside, which is x squared minus 4. Now you would think this would be fully factored, but you see here that you can factor this by using what? I'm going to bring this down. Difference of squares. So this can factor into x plus 2 and x minus 2. So now it's fully factored. But we have to find the zeros. Zeros are the same thing as your x-intercepts. So now we have to solve for x for each one, which is going to be easy. If we set this to 0 and solve for it, we'll have -2. If we set this equal to 0 and solve for it, we'll have -2. This one will have just 2. So these are our x-intercepts for this polynomial, and they're called our zeros. Alright. I see on the next one that they all have something in common, and the thing they have in common is x squared. I see this is negative, so I'm going to go ahead and take out -x squared to make it easier on me if I have to factor it again. So taking out a -x squared out of all of these would give me x squared minus 4x plus 4. And you can see now that we can factor this one out some more, because think of numbers that can multiply to get 4. That's going to be 2 and 2. But we could use -2 and -2 to multiply to get +4, add together to get that -4. And now it's fully factored. So when I set each of these equal to 0, I'll have, if I set -x squared equal to 0, you just take the square root of both sides, x is going to be 0. This one, x is going to be 2. This one, x is going to be 2. Alright, I'm going to let you try 3 on your own, so Ms. Price, if you'll pause it. Also, y'all mark out number 4, because that's the same one we did up there. So try number 3 on your own. I'll give you a clue. They have something in common, so pull that out first. Alright, so you should have pulled out an x squared. In parentheses, that would give you x squared minus 4. I hope you saw that this is a difference of squares problem, so we can pull out x plus 2 and x minus 2. And so when we set all these to 0, you should have gotten x equals 0, x equals negative 2, x equals 2. Alright, this one's a little different. It's in factored form. So this part, the factored part, is already done for you. So it's super easy. They've already put it in factored form. So from here, all we have to do is set these equal to 0 to solve for x. So this one's going to be x equals 5. This one's going to be x equals negative 4. Alright, Ms. Price, if you'll pause and let them do this one, and then when they're ready, just unpause it so they can check their work. Alright, the answer was x equals negative 5, x equals negative 2. Alright, flip it over. Alright, so now we're going to talk about zeros, which is the same thing as x-intercepts, what we just found. And their multiplicities. Okay? First, let's do this one together to find all the zeros, and then I'll explain the multiplicity of each zero. So this one, when we set x to 0, or excuse me, set this equal to 0, we'll have x equals negative 2. For this one, we'll just get 1/2. For this one, we'll just get 5. Okay? The multiplicity, each zero has its own multiplicity, and it has to do with the exponent on the outside. So for example, let me go back to here. On this problem, that x minus 2 times x minus 2, we really could have just wrote that as negative x squared and x minus 2 squared. Right? This is the same thing as squaring it. I just wrote it out fully. Because you can see from here we just get x equals 2. Same thing we got here, we just got it twice. So the multiplicity of this 0 is 2 because it appears twice. This one, they could have wrote it out like this. Negative 4 x plus 2 x minus 1/2 times x minus 1/2 times x minus 5 x minus 5 x minus 5. They didn't though, because what's the point of writing it out when we can write it like this? The point of me writing it out like this in the last few problems is so you can see how many times they appear. That's called your multiplicity. So basically the shortcut, what's the exponent of this one outside? 1. So this multiplicity, this negative 2, the multiplicity of it is 1. The multiplicity of 1/2 is 2 because of that exponent. So the multiplicity of 5 is 3. And why is this significant? Because on your graph, your multiplicities decide whether you break through, and this is what I mean by break through the x-intercept, or whether you hit the x-intercept and bounce back and go the other direction instead of breaking through. When it is an odd multiplicity, like 1, 3, 5, 7, you are going to break through. So write odd, break through. If it's an even multiplicity, like 2, 4, 6, even, you're going to bounce. Or they use the word, I think they used the word, no they didn't. So if it's even, you're going to hit the x-intercept and bounce back off of it. That's why multiplicities are important. We'll get to that when we start graphing next chapter on Tuesday. But for now, I just want you to find the multiplicities of each 0 that we found on this page. Okay? So for example, our answers for this first one is negative 2 and 2. So x equals 2 and x equals negative 2. The multiplicity of x equals 2 is just 1, because we set this one equal to 0. So basically you only see x minus 2 in here once. We only got it once for an answer, so the multiplicity is 1. Which means it is going to break through the graph. because it has an odd multiplicity. This negative 2, you remember that we found that twice here, so it has a multiplicity of 2. Mult 2, oops, which means it is going to bounce off the graph. Alright, I want you to do the rest on your own, and then Ms. Price, if you'll pause it and then play it when they get done so they can just check their work. I'm just putting an M2 for a multiplicity of 2. We marked out 4. Here we got x equals 5m1. Alright, I hope y'all have a great weekend. We will pick up here on Tuesday.